Okay, 8.3 is rational functions. And the big thing to remember again with this one is that rational just means that it's a fraction. And what we were doing in sections 1 and 2, especially in section 2 when we were doing the inverse function or the reciprocal function, it was still a fraction, so that was just another example of a rational function of this. And we're going to get some definitions here at the front, so this is one of those things where we're just going to have to kind of keep your notes handy when you're going through this, because it's going to ask you for some things off this. So first thing we've got is a continuous graph. If it's continuous, what does that mean? Goes forever, right? Yeah, it just keeps going and going and going. So if it's a continuous graph, it goes forever. And here's the big thing that kind of goes with this one is, if it's continuous, there are no skipped values. And what we're going to kind of look at in this section is if we skip a value, we put a hole in the graph because we jump around it. So that's kind of what we're looking at. So continuous graph means that there are no holes in the graph when we're looking at this thing. Okay, which means once you put your pen down or pencil down on a piece of paper and you start graphing it, you never have to pick it up until you go off the edge of the paper. If it's got a hole in it, that means you're going to stop and go around it, put something around a spot when you're going through there. Alright, this one not necessarily a definition, it's more just kind of a little update here. When you're talking about the domain is all real numbers except for the denominator equals 0. And that's something we've talked about it before, but again, it never hurts to go back and just to mention it again. So when we're talking about the rational functions, it's all real numbers except for whatever makes that denominator equal to 0. So not really a definition, more just a reminder on that one. Alright, second definition, second kind of new thing here, is a discontinuous graph. Well, if continuous meant we go forever and there's no holes, if it's discontinuous, this means not, right? It's not continuous, which means it's going to not have no holes, which means it's going to have holes in it. So discontinuous, that means you're going to skip values. And where you're going to skip values, which means it has holes. And those holes are going to be where the denominator equals 0. So continuous graph goes forever. We don't skip anything at all. There's no holes in it. If it's discontinuous, which means it's not continuous, it means you're going to skip over some numbers. You're going to have some gaps in the graph. And those gaps are what they call holes. Now here's where we're going to put a definition kind of with a definition, because this part kind of goes with the discontinuous graph here. When we skip those values, so whenever you skip over a value when you're going through these, they're going to call those points of discontinuity. So that's a mouthful. That's why I would just, the standard version is we call them holes. The technical mathematical term is a point of discontinuity, which hole is just a lot easier to say. So that's why we call them that. Okay. Now with that one, again, sometimes they call them holes. You want to do an AKA here. Sometimes they call them holes. Sometimes they call them vertical asymptotes. Because a vertical asymptote is a little different than a hole because it's actually like a wall that you can't touch. Vertical asymptotes are the same thing. That's numbers that you skip over. It's not actually part of the graph. It's more like a cutoff. Okay, and then two more definitions. First one we'll do is removable discontinuity. Okay, so for removable discontinuity, basically is what this is. It has a, we'll say a variable expression. That can be canceled, or as they like to say, removed. By factoring. All right, let me just give you a quick example of that, and then we've got one more thing we've got to do. One more definition. Okay, so here's some examples of some things we're going to work with in this section. Maybe they give you something like this, where you have f of x is x times x plus 1, and that's over x minus 3 times x plus 1. Okay, now again, we're flashing back to chapter 2, I think it was for this one. That if you're doing this, you can factor out, or you can cancel out the x plus 1s, and that'll leave you with x over x minus 3. And since you canceled out the x plus 1, then they're going to say, all right, well, canceling is the same thing as removing. So since we removed x plus 1, then we're going to set that equal to 0. And for that one, just subtract 1 from both sides. So that would be negative 1. So when they ask for, and that basically that's going to mean that there's a gap, there's a hole, there's something in the graph that's going to happen at negative 1 when we're going through this thing. So whatever it is that you cancel out or you remove, you set that part. Now, if you have two things that you cancel out, you'd have two things that would equal 0. And now somebody may be asking, all right, well, you know, we're talking about everything in the denominator. What about this x minus 3? Well, that's kind of the next thing they throw at you here. So that x minus 3 that's there, they call that a non-removable. Discontinuity. And if removable means you can remove it, if it's non-removable, that means you cannot remove it. Again, when they're talking about removing, they're talking about canceling. So for this problem, that would have been x minus 3. Again, just set that equal to 0, so that's x minus 3 equal to 0. So that's x equals 3. So if you cancel something out, they call that a removable discontinuity or a removable hole, or whatever they want to call it there. If it's something that you cannot cancel out and it's left over in the denominator, well then they say that's non-removable because it was left over. So, but you still set that part equal to 0. Okay, and then the last two things we'll look at. We kind of talked about vertical asymptotes and horizontal asymptotes in section 2, just about what they were, and we put the lines there. This one we're going to dig into them just a little bit deeper. And again, as we're talking about the horizontal asymptotes, we'll just call it HA for short, so we don't have to keep saying that over and over. And on some of these, they're going to ask you, they're just going to give you an equation, and they're going to ask you, okay, find out, or this fraction, this rational expression. They're going to say, all right, tell me what the horizontal asymptote is. And we're going to do horizontal asymptotes first because it's the hardest one, because it's more of a check thing that you have to do. And then vertical asymptotes, it's pretty straightforward. So we'll be okay with it. But basically, here's what it is. Here's the setup for this thing. If the degree of the numerator which we're going to call m in this case, and the degree of the denominator they're going to call n, and here's what you're going to do. You're going to compare them. Everybody knows what we're saying when we talk about degree, right? Flashing back to chapter 4, I think it was. You know, when we went through those parts, what is the degree? Highest power, right? Yeah, so when we're talking about the degree, it's just the highest power of whatever you have in the numerator, and it's the highest power of whatever you have in the denominator. And you compare them. You only have 3 options if you compare numbers. 1, the numerator, which is degree, is less than the denominator degree. So m is less than n. And if the numerator degree is less than the denominator degree, then it's going to be really simple. The horizontal asymptote is going to be at y equals 0. So it's just the same thing it was back in the earlier problems when we were doing back in section 2, that this thing would be right on top of the x-axis. Okay, so either the numerator can be less than, those two things could also be equal, right? So if the numerator degree is the same as the denominator degree, the horizontal asymptote is going to be a little bit more work on this one. Y equals, and it's the leading term of the numerator over the leading term of the denominator. Because basically your powers of x are going to be the same, so they're going to cancel each other out. And if they cancel each other out, then you're just left with whatever numbers you had in front. And only one other option left. If it's either the numerator is less than, the numerator is equal, or on the flip side, if the numerator is greater. Because that's the only three choices you have. It's either less than, equal, or greater. And for this one, if the numerator is greater than the denominator, there is none. So this would be an option where they'll have to, in the homework or any test questions we do, there'll always have to be a second choice for what it's going to be. Tell me the horizontal asymptote is y equals something, or option B is there's not one. So there'll always be that option that you may not have one at all. All right, now let's just show you an example of what we're looking at here. All right, and the directions should look something kind of like this. That they're going to tell you state the horizontal asymptote if it exists. Because, again, you get option 3 that it may not be there at all. And they'll just give you an equation. Here we go. Let's go negative 2x plus 6 over x minus 5. All right, now here's one where, again, try not to make the easy stuff easy. What is your highest power term in the numerator? Just x, right? Again, that technically x is x to the first, so your m value would be 1. Denominator, same thing, right? That's technically a 1, so that means that the n value would also be 1. And if you compare those two numbers, they are equal, right? Because 1 equals 1. So if the two powers are the same, that means we're going to have to do option 2, right? So now we're going to take the leading term that's here, which is the negative 2x, and put that over x. And when you do that every single time, again, if you'll put a 1 here, those will always cancel each other out for the x's. Oh, yeah. There we go. So you're just going to take the first two terms you have, take out the x's, it's negative 2 over 1. That's just negative 2. So you would have a horizontal asymptote at y equals negative 2. All right, example 2. We'll do the same thing here. We're not going to rewrite the directions because it's going to be the exact same directions here. And again, these once you've got the directions, once you've got the steps back up here, the things you're looking for, it's really not that bad. It should go pretty quick. Okay, so for example 2, we're doing x minus 1 over x squared plus 4x minus 4. And all you're trying to do to figure out what the asymptotes are is you're going to look at the powers. Top one, you've got x minus 1, so that's x to the first, so that m value is 1. This one you have x squared, so your m value is 2. So if we compare m and n, m is less than n, right? Because 1's less than 2. That means we're doing option 1. And option 1 said you don't have to do anything at all. You just tell me it's y equals 0. And most people like that one because they're like, oh, I don't have to do anything. No, because if the numerator power is less than the denominator, every single time it's a default answer, it's y equals 0. And really the only one you have to do work on is option 2. If these two powers are equal, you just have to cancel out the leading two terms and see what you have left over. All right, and one more, because there's only one other option you can have. Let's go with x squared plus 2x minus 3 over x minus 4. Okay, so for numerator on this one, highest degree term is x squared, so the m is 2. On the bottom you have just the x, which again technically is x to the first, so you're, oh, sorry, that's a 1. And then you're going to compare m and n. So that's 2 and 1. 2 is greater than 1, so if we're going greater, that means we're going option 3, which means there is not 1. Not there, NA, whatever you want to call it. Not available, doesn't exist. No solution. Whatever you want to call it there, they're going to give you the option. Again, it'll be that one they have to kind of give you a bullet there. And it may say it does not exist or something like that.
How do you get
Oh, that when we're going. Alright, and the last thing we've got to do is vertical asymptotes. And these are a little bit easier than horizontal because you don't have this option 1, option 2, option 3 where you compare these. There's really just one, well, sort of two things you do. You have to factor the denominator. If it's possible. And cancel. Expressions. Comma, if it's possible. Because sometimes you can, sometimes you can't. It just depends on the problem. So vertical asymptotes, you factor everything out as much as you can, and then just see if there's anything you can do that you can cancel out of it. Once you've factored and canceled, if it's possible, you set each expression in the denominator equal to 0. And that's it. That's all you have to do. And most of the time, you're not. It's about 50-50. Half the time you'll have to do some factoring. The other half of the time you won't have to do any factoring. You just take the denominator and set it equal to 0. So there's no checklist on this one. There's no 3 options. It's take the denominator, set it equal to 0. That's all you got to do. All right. So let's show you 2 or 3 examples here, and then we'll wrap this thing up. We've got x squared minus 2 over x plus 1. Okay, yeah, there's nothing you can do to factor the denominator, so it's pretty much stuck here. So for that one, you just set x plus 1 equals 0. There you go. So x plus 1 equals 0, subtract 1 from both sides, x is negative 1. There you go. That's all you have to do. All right, let's just show you a couple more. Because most of the time, if they're not that fast, then you can usually get them somewhat closer to that. Okay, for example 2, make it a little bit longer. Let's go with x minus 3 over x plus 4 and x minus 3. Okay, so this one, denominator's already factored out for us, so we don't have to do anything there. Now you're just canceling. Cancel the x minus 3's, which means you're left with x plus 4. So x plus 4 equals 0, so that's x equals negative 4. There's your vertical asymptote there. Now, here's a little side note for this one, because they may ask for this on some other things. Here's just a little extra piece here. Here's a bonus. Well, we'll call it a bonus, but it's not really a bonus thing on this one. Because we canceled x minus 3, right? So if you set this equal to 0, that's x equals 3. That's what they're going to call a point of discontinuity, or as we like to call it, a hole. Discontinuity. Okay, now if they're asking just for the vertical asymptotes, that's your answer here. But some of these they may also, I think there's a question or two they're going to mix in to say, you know, list the vertical asymptotes. If you have any points of discontinuity, name those as well. So if we cancel off these x minus 3's, set that equal to 0, and then there you go. There's your holes. Or as they like to call it in mathematical terms, that's a point of discontinuity, which is just fancy for it's a hole. All right, one more of those and then we're done. Because so far you haven't had to factor. Let's give you one where you actually have to do a little bit of factoring here. So let's go with x minus 2 over x squared plus 5x. Okay, and again, top part, we're not necessarily worried about it. The only thing we really have to worry about is what's in the denominator. So we've got x squared plus 5x. Yeah, we don't have that third term, so we don't have any factors of this that equal 5 because there's nothing here. So what do those two things have in common?
They both have an x.
Both have an x. So we're going to do x squared plus 5x equal to 0. We're going to factor out the x. And if you do that, if you take 1x out of the first term and 1x out of the second one, you're left with an x and then just the 5. And now set both of those equal to 0. So that x would equal 0 and x plus 5 would equal 0. There you go. So we got that one, right? Because we got the x equals 0. When you subtract 5 here, you also get negative 5. So in this one, because it was x squared, we now have 2 vertical asymptotes in the denominator. So one here and one there. So if you get something that you can factor and nothing cancels out, like this one did, because if you factored the x minus 2, it would have been x times x plus 5. If those things don't cancel out and we've got 2 parts in the denominator, then you're going to have 2 vertical asymptotes.